Right, well, good morning, everybody. Thanks to Kenny for giving me the opportunity to kick this talk off. Initially he said, it's an 8-minute talk, no worries, I'll just give a little talk. I thought, what shall I do? I know, something a really attractive specimen, this brittle star here, I'll just talk about that. And then he got back to me and said, how about talking for 25 minutes? I thought, ooh, okay. And I thought, well, these particular amazing specimens you can see here look like starfish. They're a type of starfish, but they're actually a brittle star. A part of an amazing formation in Western Australia, which people sort of vaguely know about, but I don't think many people have seen the whole range of fossils that occur in it, and they're spectacular. And this links in a way nicely with what Di was saying earlier with the new museum, in that many years ago we were donated, thanks to a man called Mark Creasy, an enormous slab of this particular rock with an amazing range of echinoderms on it. That's going to go in the new display, I understand. So quite a few of you who work in the museum will have walked past it. It's covered up, it's got a lid on it, and you might have peeked underneath. What I want to do is just tell you a bit about these fossils. It's a bit of a slideshow showing you some of this spectacular material, but as I started putting this talk together, I came to realize it's actually an incredibly important horizon in the whole evolution of echinoderms. So it's not an area that I normally study, so I can't get into it in too much depth, you'll be glad to hear. So it's an overview, and you'll see the potential for the research that should be done on this, one of many amazing, particularly invertebrate paleontology faunas in this state, about which we don't actually know a great deal. Now, there is this rather delightful term that's bandied around a bit called echinoderm meadows, because in certain environments today, you find areas that are incredibly rich in little but echinoderms, particularly in very high latitude around Antarctica. And so just a couple of pictures I've got off the internet here. Whoops, sorry. One showing huge amounts of starfish is here, not a meadow, it's on rocks, but you get the idea. Lots and lots of starfish and very little else. Here's an area, this is probably off Antarctica, with, these brittle stars and some echinoids or sea urchins, plus a lot of scallops. What I want to argue, and others have also argued this, is that in the fossil record you find these fossilized echinoderm meadows. And the deposit I want to talk to you about today is one such fossil echinoderm meadows, and I think one of the best there is in the world in terms of its preservation and its significance. This is the block. Now, I'm really pretty rubbish about putting scale on all of my drawings, I apologise. It's probably, I don't know, a couple of metres across, Michael? Something like that,
yeah,
isn't it?
A bit more, I think.
Yeah, a bit more, 2.5 metres across. It's a huge slab. And you can see there are these strange objects on it, look like something that's come from outer space. So there's a lot of this thing here. This specimen has been prepared to a certain degree, and I'll talk about the preparation and who did it as I go along. But you'll see quite clearly here, it's a starfish, a big 5-pointed star. It's an echinoderm. These things here are a type of echinoderm. Here's another strange stem here with side branches. That's another echinoderm. The slab is almost entirely echinoderms, and that is symptomatic of this particular deposit. The deposit is called the Cundligo Formation. It's a Permian deposit, and I'll show you a map in a moment. But that's a lot of sort of, the bird's eye view, the drone view, if you like, looking down on a Paleozoic sea. If you get down with your snorkel in the Permian and you get up close and personal, this is what you would see. Here's the big starfish, and these starfish are very large. They get to the size of sort of dinner plates. And these other echinoderms here going off into the distance. So the deposit is in the southern Carnarvon Basin. It's here, the 5-pointed star, not surprisingly, marks the spot. Basically, it's in Gascoigne Junction. It's about 1 kilometre from the pub, which is very convenient, largely outcropped in and around the riverbed. Now, I won't go into this in too much detail, but it's an area that's now quarried. It's quarried by a fossil or mineral dealer, and people have different views about that. My view is such that because of the work this guy is doing, and I'll acknowledge him later on, we're seeing all this material, and he's being very good at making a lot of this material available to us. If he wasn't doing this, we wouldn't know about any of this. So this is quite a nice example of where I think as academics can work in with commercial dealers to the benefit of everybody. Okay, a bit of stratigraphy here. So we're in the Permian. The end Permian is at about 250 million. We're in a part of the Permian, we're at the end of the early Permian at a stage known as Congurian. So we're looking at rocks, and here's the Cundligo Formation here. So we're looking around about 278 million years ago that these things were living. There's a very good biostratigraphy which enables us to date this deposit reasonably accurate. So we know where they fit in, so we can correlate them with equivalent ones around the world. The deposit itself is, people tend to say it's a siltstone. It's actually a very fine-grained sandstone. And work shows that the sandstones vary a little bit. They have a lot of structures within them. There are these terms, swaley cross-bedding and hummocky cross-bedded sandstone, which sound very quaint, sort of old English terms, but they're very important because they tell us something about the environment of deposition. If you have hummocky cross-bedded sandstones, the inference is that these formed under storm deposits, where a lot of hydrodynamic activity, the sand's being churned up, it's being deposited very rapidly. So these animals are living in a very high energy environment, and that is the reason for their preservation. Because all these specimens I'm going to show you, they're catastrophes. You've had these animals living quite happily on the sea floor. There's been a major storm, cyclone like one going through up north at the moment, and they're just smothered by the sand. They're dying in situ, they're being fossilized in situ. Because a lot of echinoderms will naturally just fall apart after death. If they die in normal circumstances, then the soft tissue that holds the individual plates together that make the animals fall apart and the things just disintegrate. Here we have whole, complete specimens. We know exactly what that biota was. We also have indication from the sediments themselves that it was a storm deposit, because one of the other characteristic things that you find are things called mud clasts. So this is a chunk of another specimen. You can see the little arm, tantalizing arm of a starfish coming in here. I'll show you the whole thing shortly, all will be revealed. The rock is slightly sparkly fine sandstone. There's a lot of mica in it, so you know it's a relatively coarse, but you see there are these black blobs. There's one here, there's a whole mass of them here, there's one here. These are called mud clasts, and these represent where, you know, on the sea surface, when the conditions are very quiet, mud would have settled. It starts being held, it's held together by probably bacteria, microbial communities. Storm comes and rips up pieces of this mud, which then get flipped around and get incorporated in sand. So when you see mud clasts, that's another indication that this is a storm deposit. They're quite convenient. Okay, quick refresher course for you who may not be totally au fait with your phylum Echinodermata. The Echinoderm classes that were around in the Permian are the same as the ones that are around today. There used to be loads of other ones back in the early Paleozoic, lots of sort of evolutionary experiments that all disappeared, and we were left with the 5 here, the great survivors. There are the crinoids, or sea lilies, the asteroids, starfish or sea stars, ophiuroids, or brittle stars, echinoidea or sea urchins, and the holothuriidea or sea cucumbers. Now most of the work that I've done in my life on echinoderms, as Kenny mentioned, has actually been on echinoids. I've done very little on these 3 groups. I'm talking about something I don't know too much about, which may become obvious. So within this deposit, as you can see from the little star here, we have lots of brittle stars, starfish, and sea lilies. No echinoids. I think there's one fragment of an echinoid from the Paleozoic of Western Australia. They're just not preserved. Holothuriids, or sea cucumbers, tend to fall apart after death, and the hard parts are just isolated little ossicles, which are around in sediments, but nobody seems to really study them very much, fortunately. So, the 3 groups. So I'm going to go through each of these groups in turn and talk about the significance, but show you to some of these amazing specimens. Within the Cundligo Formation, there are certainly 3 known species. So even though there are loads of specimens, it's not species rich. This is from a deposit that may or may not be the Carnarvon formation. This form here, Archaeoisocrinus, is known from just a single specimen. Neocamptocrinus, there's quite a lot of them, but 95% plus is this thing, Jumbocrinus bostocki, described by Kurt Teicher in 1954. And here's a classic example. This shows you the morphology of the crinoid, and just a refresher, or to let you know about crinoids. They're called sea lilies because they look like plants. Sea tulip in some ways would be more appropriate, I think. So they have a stem which they attach either by some anchoring, by cementation, or literally root-like structures going into the sediment. They have a long stem here made up of single little ossicles. Then there's the main calyx, or the cup, made up of circlets of plates. And then these arms, often 5 arms coming off with little pinnules on them. And these are very flexible, and they wave these around. They secrete mucus, they trap planktonic material from the water, pass it down into the mouth, which is located down here. Firstly, Archaeoisocrinus. It's a single specimen. This is an appalling photograph, I do apologise. I didn't have time to get a better one. It was found nestling inside the arms of one of those Jumbocrinus specimens by Peter Gell and Webster when they described some of this material in the late 1990s. What they argued is that this is the earliest known articulate crinoid. This says nothing about how well crinoids could speak. It's just due to the structure of the crinoid themselves. But all modern crinoids are articulate crinoids. Before that, you had other groups in the Paleozoic, so there was a big changeover. They argue that, as I say, that this is the earliest of all the living groups. Now, looking at some recent papers, I'm not sure that everybody agrees with this, and I'm in no position to judge, but this is their argument. 1 or 2 other people have supported them on this. So we have potentially the earliest of the modern crinoids occurring in this Carnarvon formation near the pub in Gascoigne Junction. And here's a modern isocrinid, which are very interesting, have an interesting story in their own right, in that they tended to become, a lot of them in the fossil record, they disappear at the end of the Cretaceous in the Northern Hemisphere, but they linger on in the fossil record well into the Miocene in this part of the world. And you can see this is how they live. They've got a stem, very small cup, and lots of arms hanging off. So that's a typical isocrinid. Now the second one, Nurseocidentalis occidentalis, is an amazing crinoid. Now you saw from those previous photographs, the stem is going straight up. It's like a plant growing out of the soil, upright. That's how most crinoids live. Now, what have we got here? We've got a slab with this, don't look at that yet, ignore that. We can ignore this strange crinoid here as well. This is what we're dealing with. This is Neocamptocrinus. If we started this end here that would have been cemented, it goes along here. And the nature of this particular column is that unlike most other crinoids where the column is circular cross-section, this is very flattened along here. It's flattened, and it's got some odd side branches coming out. I'll show you another slide a bit clearer next. As you proceed up this column, the column stops being flattened and becomes circular. And here's the cup and the little arms that are radiating off the cup. This is another view of the same specimen, and it sort of shows it in life position. And to me, it's like a cobra rearing up. And I think that's how they actually live. That was their orientation in life. So here you can see the flattened stem with these side branches. So I think almost certainly, rather than being vertical, this part of the stem was horizontal. It was lying along the sediment. To say this is very turbulent seas these things are living in, this would help anchor the thing into these sediments. So it's flat, 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 and then as it rears up, it becomes circular, and then it flexes around and goes in this direction. Now, there's a very convenient drawing done by Adolf Seilacher, who did some amazing drawings of fossils, reconstructions, that shows a very similar morphology in a Devonian specimen, and you can see it here, and he's drawn it in that same way as well. I came up with this how I thought it was before I saw this, so we've both come up with the sort of same idea. So it's doing the same thing. Here, the side branches on this one don't come out laterally, they actually, he has them reconstructed sticking in the air, so it is a bit different. But by and large, it's the same morphology and probably the same lifestyle. So he has a current direction going this way and the thing pointing in that direction. You could argue maybe the things are actually pointing the other way to take advantage of the current. Don't know, something to think about. Anyway, so that's Neocamptocrinus. Going on our little snorkeling expedition, down, and we look closely at the common one, the most common crinoid, is Gimbocrinus. This is a big thing about the size of a golf ball generally, and you can see it has these large spines sticking off it. Here's a cup here, or the calyx. Here is the stem, so it's rather twisted in on itself. Here's the round stem, which presumably was upright. Here's the cup, and here are the arms, and you can see the beautiful detail that's preserved on this. These specimens have all been prepared by air abrasive, and these are by a couple of the guys that Tom Capitani employs, who I'll mention them at the end. But the specimens that we've seen over the years that Tom's produced, the quality of this preservation has got better and better, and they've become really, really talented at preparing these things and not destroying any morphological features. They really know what they're doing, these guys. So we have a slab here, which is looking closer at the big slab that we've got that's going to go on display. And you can see here's the calyx and the arms, and there's the stem, there's another one. This has been only partially prepared. This is quite early on when they didn't prepare further than that, so they're sort of nestling down within the sediment. Now if you look at it, some years ago I thought, this is interesting. The orientation is really quite strange, because why are they not, you've got the column here, why isn't this thing going straight up, then the arm's going straight up? You think, oh well, it's been thrown around in storms, and this is what Tycho said when he described it. He noticed this and said, oh, this is a post-mortem thing. These things just get a bit twisted after they die. Well, there's another specimen that Tom made available for us to look at last year. And you can see this amazing slab here. You can see the starfish, brittle stars, which I'll come to. But these incredible, it's a bit of a mass of crinoids, but they're all nearly complete. I put an arrow here pointing to the junction between calyx and the stem. And you can see where I've got it in red, there's always this really tight turn. It's about 130, 135 degree bend over. That one, that one, that one. I think there's 10 of them. They're virtually all like that. There's one that isn't. This one seems to go straight in. So I wonder whether this was actually how it was in life, or it was able to be so flexible that in life it could be like this. And in some ways, again, it's then like the Neocamptocrinus, in that it had an upright stem, but it could angle itself and face either in or maybe away from the currents. Maybe away from the currents, eddies would perhaps bring the food into the mouth. But I think quite possibly it's a morphological feature. But this is just one of the many things that needs to be studied in detail. And there are a lot of these slabs that have been produced, they're available for sale, and a lot of museums have them. We've got quite a lot here. Somebody just needs to sit down and go through them all and just do a bit of science on this. But it's a very intriguing aspect. Okay, let's look at the ophiuroids, or the brittle stars. Brittle stars basically are like starfish. They have their arms and they have a central disc. Now the central disc in this particular one is like this large web-like structure. Most modern day, virtually all modern day brittle stars, it's just a very small compact disc right in the middle. So this one's very different, and that's because it's part of an ancient group, a different group. This is the best slab we have, which unfortunately I don't think is going to go on display. I'm sure if you ask Michael kindly, he will show you the specimen, won't you, Michael? I do actually have a scale on this one, that's 10 centimeters. And what you can see is there's a brittle star there, one there, one there, one there, one there. And really quite cute. These things seem to be touching the ends of their arms. It's almost as though these things are getting a bit emotive about this, dancing their way across this slab. Just hone in a bit closer. Ab means the aboral view, that means the top view, so that's looking down on one of these brittle stars. Oral view means the underside where the mouth is, so these ones are different orientations. So they've been flipped over during the storm event. Here, this one is the other way up. When I asked Tom about this, he said he prepared this was the way up. So this one would have been actual orientation like that. This one has been flipped over, this one's been flipped over. Flipped over, but they haven't been sort of broken apart by the activity of the currents, and then quickly buried by the sediment. And you can see in this all these mud clasts over here. And these are the other two. This is an oral view, so this is on the underside. This one's a bit half and half. It's sort of oral view, but this arm here is flipped over, so it's going to be contorted. Now, these particular ophiuroids are an ancient group. They appeared, all ophiuroids appeared in the early Ordovician, and they're lumped together in one group called Stenuroidea. Now, everybody that works on these things has a completely different classification from each other, so I'm not going to get into that at all. But basically, you have the Paleozoic archaic types, which are rather sort of cumbersome organisms. Then, in the late Paleozoic, you had the evolution of much more flexible, the modern ophiuroids. What makes our specimen here from the Conliga formation, this and this, very important, is that this is the youngest known of these archaic ophiuroids. It was thought they became extinct at the end of the Carboniferous. Here we've got them lingering into the Permian, but they overlapped in time with the modern group. The modern group, as it says here, were probably more flexible. They evolved a more flexible morphology. And one argument is that maybe at the latter part of the Paleozoic, there was a rise of a lot of predators, so-called durophagous predators, predators of shells, things crushing up shells. And that those forms that evolved a much more flexible skeleton were more likely to be selected. The older type that were less selected, maybe these were the ones that eventually became extinct. This shows that the range of all these early stem group archaic ophiuroids from the early Ordovician, lots of them in the Ordovician Silurian, start tailing off in the Carboniferous. That was the last known one until we realised what this was way up here at the end of the early Permian. When you plot the latitudes of these, and you go from down here in the Mississippian, the Carboniferous, early Carboniferous, the red are the archaic types, the black are the newly evolving modern types. They coexisted in low latitudes. Here, later Carboniferous coexisted in low latitudes. Western Australia at the time of this deposit was in a high latitude. So the only one we have preserved is a high latitude. In lower latitudes, there are no more of these archaic types. So maybe they've sort of been pushed into or gone into the higher latitudes, perhaps because of higher predation pressure in the low latitudes. Just an idea that needs to be tested. When you get up in the Triassic, you can see in the early Triassic, they then start spreading out into the higher latitudes somewhat. Here's a fossil of a modern one, and here's our archaic gentleman. And this is just this amazing one of the amazing slabs that Tom has. And you can see that basically they're in layers. There are layers of these things. There are so many of them. And that's very analogous to a lot of the kind of meadows you see today, where you can get these thousands and thousands, millions of ophiuroids, brittle stars living together. So the last group, the asteroids, starfish. Here's a lovely little starfish clinging to this rather alien-like Jimbocrinus. 2 minutes, okay. Big dinner plate size guys. This is undescribed. I'm sort of working on it with a guy called Andy Gale in Britain. We've been working on it for a while. There is a similar form known from the overlying Montague Formation in the Carnarvon Basin. This is different though. The plating structure is slightly different around the mouth. It's a group called the Monasterids, so we suspect it's an undescribed genus. And there's the top surface, which shows similarities but also dissimilarities to this other form known from WA. Here is another of Tom's new slabs. There's one there, there's one there, there's one there, there's one there, there's a tiny one there. And here you can see somebody's finger pointing how small some of these specimens are. So we've got a really nice growth series of these things. So we can look at the ontogenetic development from fingernail size up to dinner plate size, and you can't normally do that with this sort of material. And here's me putting it all together, and what it shows is that with the crinoids, you have basically some of the last of the camarates, but you also have this first possible articulate, first of the modern crinoids. This is a late camarate, which are the, sorry, there's an E missing there, the Paleozoic forms. With the ophiuroids, it's the last of the archaic group, and with the asteroids, there's a gap in the fossil record. Somebody's just described a new genus from early in the Triassic here, but they make the point that there really are no very late Permian starfish, so there's a big gap here. So our form here is one of the last of these Paleozoic forms. So many thanks to Tom Capitani, who has made a lot of this stuff available to us. Some has been purchased through the assistance of David Vaughan, by Mark Creasy, who's donated this material to the museum. Andrew Walter and Ralph Walter are the people responsible for doing this amazing preparation of the material. And thanks also to Andy and Aaron, who've done the work, most of the work, with me on the other members of the group. And that's it. Oh yeah, just to plug this amazing book that came out 2017 on Australian Echinoderms. If you haven't seen it, see it. There's all chapters in there co-authored by Lizette Marsh, me, and there are a lot of Clay Bryce's photographs in here. It's a fantastic book. Thank you.